Okay, let's talk batteries. I mean, they're everywhere, right? In our phones, our laptops, our cars. But have you ever thought about how they're actually made? Well, it turns out that behind all the high-tech chemistry, there's a surprisingly simple foundational step, a kind of secret recipe. And getting that recipe wrong, well, it messes up everything. So today, we're going to pull back the curtain and look inside the perfect mix. So, I've got a question for you. What do you think is the single most important part of making a really great battery? One that charges super fast and lasts forever. Is it getting the rare materials like lithium? Or maybe it's the fancy high-tech assembly in some sterile clean room? Well, the real answer is probably not what you're thinking.
It's the mix. That's it. Before anything else happens, all the raw materials have to be blended into this perfect, totally uniform slurry. Honestly, the best way to think about it is like pancake batter. If your batter's lumpy, it doesn't matter how expensive your frying pan is, you're gonna get a bad pancake. It's the exact same idea here. The mix is everything.
And, just like any chef will tell you, a great dish starts with getting your ingredients ready, what they call the mise en place. So let's take a look at the 4 key ingredients that make up the batter for every single lithium-ion battery out there. So here's the team. First up, you've got your active material. This is the star player, the powder that actually holds and releases the energy. Then you have the conductive additive, which is crucial for making sure electrons can move around. The binder is basically the glue that holds all the solid bits together. And finally, the solvent. That's the liquid that everything gets mixed into.
Okay, so let's translate that into kitchen speak. The active material? That's your flour, the main event. The conductive additive is like a microscopic web of wiring woven all through it. The binder? That's your egg, the glue holding the whole thing together. And the solvent is the milk or water, the liquid that turns all those powders into a smooth, workable batter. Sounds simple, right? Well, mixing them perfectly is a whole other story. Yeah, you're not going to just grab a bowl and a whisk for this job. Making this battery slurry requires some seriously specialized high-tech machinery. Think of these as the ultimate chef's tools for the battery world.
And the undisputed workhorse of the industry is this beast, the planetary mixer. Now, this isn't just a bigger version of the stand mixer you might have on your kitchen counter. Its design is pure genius, and it's absolutely necessary for handling the incredibly thick, kind of sticky slurry that becomes a battery electrode. So what makes it so special? It's this brilliant dual motion action. The blades themselves rotate on their own axes, sure, just like a normal mixer, but, and this is the key, the entire gearbox also revolves around the inside of the pot, kind of like a planet orbiting the sun. This 1-2 punch means there are absolutely no dead zones, nowhere to hide. Every single particle is forced into the action, guaranteeing a perfect mix. So you've got your ingredients, you've got your high-tech mixer. Now comes the art of the mix itself. This is where pure technique and precision take over. It's this incredibly delicate dance between speed, time, and the final consistency.
The number one objective here is something called perfect particle dispersion. See, that conductive additive, it's usually a superfine carbon powder, is made of these teeny tiny particles that just love to clump together. The whole point of all this intense mixing is to break those clumps apart and spread them out evenly, creating this perfect uninterrupted superhighway for electrons to travel on.
And the main weapon you have for busting up those clumps is called shear rate. All that really means is how much force the mixer is applying to the slurry. The faster the blades move, the higher the shear, and the more power you have to rip those stubborn little clumps of particles apart. But, and this is a huge but, here's that balancing act again. If you don't mix hard enough, if your shear rate is too low, those clumps will stay put. You'll end up with dead spots in your battery that can't conduct electricity, which just kills its performance. On the other hand, if you go too crazy and mix for too long or too fast, you can literally shred the polymer that acts as the glue. You can even crack the main active material particles themselves. It's a classic case of finding that perfect sweet spot right in the middle. Okay, so once all the particles are nicely spread out, there's another critical thing to get right: viscosity. That's just a fancy word for how thick the slurry is. And getting this right is absolutely non-negotiable for the very next step in the process, which is coating this batter onto a sheet of metal foil. And just like with the mixing force, there's a Goldilocks zone for viscosity. If the slurry is too thin and runny, the heavier particles will just sink to the bottom and you'll get an uneven coat. If it's way too thick, like toothpaste, it won't spread properly and you'll get streaks and clumps. It's only when the viscosity is just right that you can lay down that perfectly smooth, uniform layer that a high-performance battery absolutely has to have.
And all of this brings us to the final point and why every single one of these steps is so critical. Because after the slurry is mixed and coated, it gets sent into a long oven to dry, to bake. And once that happens, everything is set in stone. This isn't like baking a cake where you can maybe cover up a mistake with some frosting. In battery manufacturing, there are no do-overs. There is no fixing it later. A bad slurry is a bad battery. Full stop. And this really is the crucial takeaway. Any little clump, any tiny patch of unevenness, any imperfection that was created back in that mixing bowl gets permanently locked into place when the electrode is dried. It becomes, as the researchers put it, a permanent and unfixable defect, a flaw that will hamstring that battery's performance for its entire lifespan. So it kind of leaves you with this big, interesting question. We're always hearing about the search for some revolutionary new material that's going to change energy storage forever. But maybe the next giant leap forward isn't about inventing something new at all. Maybe it's about the relentless, microscopic, and incredibly difficult pursuit of just perfecting the recipe we already have. Thanks for watching.